Okay, so last lesson we started this as a new topic. So remember, a lot of what we actually, some of what we are doing now was knowledge that you would have covered in matrices. Okay, so we looked at graphs, and we looked at the features of a graph last lesson. So does anyone remember what a vertex and what an edge is? It's there for you, but just explain it to me. Yes, Zach. Speak louder so we can hear you in the YouTube recording.
Okay, so the vertex is the dots.
Good.
Edges are the lines that connect.
Good. So a vertex is what we refer to as these dots, and the edges are the lines, as Zach said, that connect them to one another. Okay. And we learned how to interpret the graphs in some to some basic level. We'll get into more of that a little bit later, but we at least learned how to add up the number of edges, but also the degree of each vertex. So remember, the degree of a vertex, for example, this is just referring to how many edges connect to that dot, or how many lines connect to that dot. Okay, that's what we talk about when we degree. We're talking about degrees. Now, with the sum of degrees, remember, what you're doing is you're adding up the degree of all of the vertices. Okay, that's what that means. And there's a short way of doing it. Remember, you just count. If you want to find the sum, all you do is you count the number of lines or edges, and you just multiply it by 2. Okay, and that's how you get the sum of the degrees. And we also learned, I think down here, how do you find the number of edges if you have the sum of the degrees? So we use this formula as well. So you kind of just work backwards to find the number of lines in a graph. Now, I think what you might get question-wise on the SAC is a question might be a graph has this number edges, this number as a sum of the vertices. The sum of the degrees. Tell me how many edges there might be. Okay, so just be mindful that that's how that might be used in a SAC. All right, let's get into a little bit more detail about networks. So what we're covering in 9C part 1, so this is split into 3 parts. The first part is on your isomorphic graphs. Okay, so you'll see this word pop up every now and then. Isomorphic. Okay. Isomorphic. Okay, according to this, a graph is completely determined by which edges are joined to each vertices. So if you look at a graph, okay, it's determined by what the connections are, how many vertices there might be, how many edges, and what they're connected to. Okay, and you all know how they're drawn. Obviously a graph, you've got your vertices, and then you've got your edges that they're connected to. Yeah. Now, when it comes to the word isomorphic, okay, what we're looking at here, okay, is we're looking at whether or not they're two graphs. So you've got two separate graphs. What you're trying to show, or what you're trying to look for, is whether or not they are exactly the same. That's what isomorphic means. Okay, and here are, you could say, the 2 rules that you got to abide by if 2 graphs are isomorphic. So if they're exactly the same. Now, one way that you might sort of see this is, let's say, for example, you've got this graph, and then you've got another graph. Okay, and then they might have some edges to them. Okay, and what you've got to prove or show me is tell me, are they exactly the same? Okay, now look at the 2 rules, yeah? We need to make sure if 2 graphs are isomorphic, they have the same number of vertices and edges. So right there, what I like to do is already look at the vertices. The vertices, do they have the same number of vertices? If not, then already right there, they're not going to be isomorphic. Okay, so that's one way you can look at it. So same number of vertices and edges. And the vertices, the other thing is they have to be connected in the same way. Okay, one thing to note is even though on some graphs you might label them as like A, B, C, D, E, F, the dots are the labels of each vertex don't necessarily matter as long as the connections are exactly the same. Okay, and I'll explain more of that when we do these examples here. Okay, so be mindful of those 2 rules. They have to be exactly the same with the number of vertices and the same in terms of how they're connected with the edges. Okay, all right. A couple more things as well. Let's see. So that's what I mentioned before. But Also, watch for the degrees. So the vertices have to have the same exact degrees as well. So if I was to ask you, okay, remember isomorphic exactly the same. Are these two graphs isomorphic? Yes or no? Simple. Why not, Anthony? Tell me why. Okay, they don't have the same amount of, say it again, edges. Okay, you could say that, yeah, but the connections are not exactly the same either. Yeah, so it's the same amount of edges. In this case, correct, but we'll see that here. All right, let's use this as an example. For each of the following, identify the graph that is not isomorphic to the other two and give reason for your answer. Okay, generally speaking, I like to label the vertices here. So you might want to put, for example, A, B, C. You don't have to, but it might help with the reasoning part. Yeah, I've seen it being done on some SACs, but you don't necessarily have to. Okay, but let's look at the first one. Okay, which one of these is the odd one out or the non-isomorphic? Anyone? The last one. Why the last one, Fahad? Good. Okay, it has 4 vertices. So you would say here, you'd say graph 3 is not isomorphic to, you say graph 1 and 2. And then his reasoning was because it has 4 vertices. So because it has, you can say 1 extra vertex. Okay, you could also say, actually, it does have the same number of edges. Okay, so the same number of edges doesn't always necessarily mean they're the same. You just got to watch out for, the one that I like is just checking if they have the same number of vertexes, or vertices, sorry. Okay, thank you. So that's graph number 3. Let's look at the next one. B. I might call some people out here. All right. Tori, can you tell me, out of the 3 graphs on B, which one is not isomorphic? The middle one. Okay, tell me why. Because it has 2 edges instead of 3. Okay, so you can say graph 2 is not isomorphic to graph 1 and 3 because of 1 less edge. Okay. Now again, I haven't labeled the vertices, so I can't really talk too much about what's connected to where. So I'll leave that as is for now. But for C, this one, it might be worth maybe labeling some of the vertices here. But let me ask, let's see. Mia, can you tell me, okay, this one might be a bit tricky. Which one of these graphs is not isomorphic to the other 2? Say again, sorry? The third one? Okay, give me a reasoning. Why do you think it's the third one? Not sure. Okay. Have a look at the connections. Remember, isomorphic means same exact number of vertices and same number of edges and same connections to those vertices. Okay, Anthony. Are they all the same? Okay. Okay, they all have 4 vertices. Good. 2, 3, 4, 1, 2, 3, 4 for all of them. Same number of edges. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. But do they have the same connections though? None of them? You're saying none of them? Ooh, I don't know about that. There is one. There's 2 that are the same. But which one do you think I... Remember the rules. They have to have the same connections. Even if it's arranged a little bit differently, the connections have to be the same. Okay? I'm not going to say it yet. Come on. Who can find it? Which one might it be? Huckton. Which one is not isomorphic to the other 2? The third one? Okay. Not quite. Someone mentioned, I think you mentioned the third. Or was it you? I can't remember. Okay, Anthony. Yes. Okay, why is it the first one? Okay, look at the connections of it. Yes, it's got the same number of edges, same vertices, but look at how it's all connected to one another. Okay? You've got, we'll talk about this a little later on, but it's called a cycle happening here. Okay? These guys are all connected to one another, or you could say each vertex has a degree of how much? That is a degree of 2, that's 2, that's 2, that's 2. Okay, now let's look at these ones. what's the degree for this one here? So this degree is going to be 1. That has a degree of 2. That has a degree of 3. That is a degree of 2. Okay, that's got a degree of 1, degree of 3, 2, 2. Notice how even though maybe the graph is arranged a little bit differently, okay, there's similarities in terms of how they are connected, okay, in terms of the degrees, okay, especially this one here. Okay, look at this. This has only a degree of 1. That kind of to me showed, oh yeah, I think those two might be isomorphic because they both have at least a degree of 1. Whereas everything here has a degree of 2. Okay, so you could justify and say graph 1 is not isomorphic. Sorry for the writing. To graph, what is it, 2 and 3? Because of the differing or different degrees. Okay, so you could justify it that way. So remember, there's 3 things you should look for. Yeah, the same number of edges and vertices. Edges and vertices, and then the same degrees for each vertex. Okay, that's the things that you got to look out for. All right, I think that'll be it for that one. I'm going to pause this. I'm going to get you guys to... All right, so 9C part 2. Now what we're looking at, so the last part we looked at, I think most people are getting the isomorphic stuff, which is good. Just make sure on the SAC, when you do your isomorphic answers, what we look for actually is the explanation, okay? Make sure you've written that down. Don't just write graph 2 or graph 1, okay? Give me a reason why. You have to justify it when you do these. Okay, let's look at part 2 now. Connected graphs. Okay, so a graph, according to this, is connected if each pair of vertices, okay, so might be more than one pair, but minimum each pair of vertices is connected by edges. So what we're looking here is that everything has to be somewhat connected by an edge. Okay, so let's look at some examples here. Graph 1 and graph 2, look at the difference. This is connected because each and every single vertex, you can see here, is connected to an edge, but also it's all accessible in some way, shape, or form. Like, if, for example, I was over in this vertex, I could go to any vertex I want because it's all somewhat connected. I might have to go through one vertex, but I can get to another one if I wanted to. Yeah, so connected means every single vertex there is accessible or is connected by an edge. If it's not connected, okay, that means, for example, here, okay, they're sort of disconnected in that you can't get, for example, if I was at this vertex and I wanted to go here, I can't because there's no direct connection. Okay, I can't just jump it if I wanted to. There has to be a connection there to make it connected. Okay, now that edge that I'm talking about that makes it connected, we call that a bridge. Okay, so your bridge is what connects your vertices together. We'll get into a little bit more detail, but just understand that a graph is connected if every single vertex has an edge connecting to it, but also that you can access, so say for example, I started at one vertex, I can get to another one if I wanted to by following the connections there, okay? And if it's not connected, which is what this looks like, then it's disconnected, okay? All right. Now there's a couple things you need to know as well. The bridges, sometimes when it comes to bridges, you can remove and add them to make the graph connected. Okay, so for example, in this graph, this has a bridge in it. Okay, I'm going to redraw it here just to make sense of it. So let me redraw it. Just ignore those examples for now. I'll just copy this. All right, so you've got those connections to those edges. This one here. Okay. All right, so this has a bridge because if I was to remove one of the edges, it'll make it disconnected. Okay, so it has a bridge because if I remove at least one of them on certain specific locations, it's going to be disconnected. If I remove, for example, though, this bridge or that edge, it's still connected. So that doesn't count as a bridge. Okay, So be mindful of where a bridge is going to be. A bridge is what connects the graph together. So for example, if I remove that edge, it's still connected, okay? But if I want to disconnect this graph, I've got to remove that edge, or I have to remove that edge. Okay, one of them, or one of these two, sorry, to make sure that they're disconnected. So in that sense, this graph has a bridge, or has bridges in there somewhere. Just got to find it. However, this graph here doesn't have a bridge. And let me redraw it here so I can show you why. Connections here. There, there, there. Okay, so why doesn't this graph have a bridge? Anyone want to tell me why? Why doesn't this one have a bridge? Anyone know? You could say that, yep. So all the vertices have at least a degree of more than one. Yep, so that's one reason. What's another reason? Thank you, though. That's really good. Anyone else know? Ryan, you went ahead with this exercise. Can you tell me why? Do you know why? Why doesn't this graph have a bridge?
Because you can't take one out.
Good. You can't take one out without making it disconnected. Because if I try taking this out, it's still connected. If I try taking this out, it's still connected. Okay, regardless of what edge I remove, the graph is always going to be connected some way. Take that one out, it's all connected. Okay, so make sure you understand that just because you remove one edge doesn't mean that the graph becomes disconnected. Okay, some graphs might not have a bridge in it because of what Anthony said, because of the degrees or the way that it's connected. All right, let's do these examples and then we'll do some exercises. So part A, draw a connected graph. So it has to be connected. 4 vertices, so 4 dots and 4 edges. That includes one bridge. Okay, so 4 vertices, 4 dots and 1 bridge. All right, so let's say, it doesn't say at least one bridge, but I'm just going to make it so there's only one bridge in the graph. Okay, so let's draw out vertices first. You've got to have 4. Okay, you can draw them any arrangement that you like, but because it's 4, I'm just going to, go in an arrangement of 4. And you have to have 4 edges, okay, 4 lines in this graph. So I can make my connections anyway. I might just go, there's 1 connection, 2, 3, okay, but there needs to be 1 bridge in there somewhere, okay. Now, why is it wrong if I put a line there? It's still going to be connected if I remove a bridge, okay, or if I remove an edge. So there's no, in this graph, no bridges exist. So that means I need to maybe draw it this way. Okay, why that way? Because where's the bridge now here, guys? The top, good. There's my bridge. There's 1 bridge in there. Okay, so now that's made it disconnected. I could also maybe draw it this way if I wanted to. Okay, because then I can just get rid of that, and now it's disconnected. But this has 2 bridges in it. Okay, it doesn't say how much, or it does say 1 bridge, so I think I'm going ahead there. But that way is fine. You could draw it this way as well. And that will make it 1 bridge, okay? And it's got 4 vertices, 4 edges. Okay, let's try another one. Let's do B. So this one has 5 vertices this time, so 5 dots. Okay, I might just draw them like this. 1, 2, 3, 4, 5. I think the beauty with networks is you can really draw your graph any way you want, which also makes it hard for the teacher because then it's hard for us to mark sometimes when you've all gone and done something crazy. But you don't have to arrange it this way if you don't want to. Okay, so it's got 5 vertices and 6 edges. Has to have 2 bridges in there somewhere. Okay, so I have to have 5 dots and 6 lines. So I can go 1, 2, 3 for now, and then 4. Okay, and then from there, remember, make sure you watch out of how you draw them, so that you're adhering to that rule of however many vertices and edges, and it's got 2 bridges as well, yeah? So watch out for that. So that means I need to be able to rub off or remove 2 edges to make it into a disconnected graph if I wanted to, okay? So I could add 1 maybe here. Okay, what have I got now? 1, 2, 3, 4, 5. So I need to add 1 more edge in there somewhere. Okay, does anyone want to add an edge anywhere? You do, yes. Is this way? Just something like that? You can totally do that. Okay, now because this has 2 bridges. Where are the 2 bridges, guys? Bottom 2 lines. Good, because I can rub off that one. Now it's disconnected. I could rub that one off, and now it's disconnected. Okay, again, it depends on how you arrange your dots and lines, though. Yeah, so just watch out for that when you do these. Cool. I think that's it for this 9C part 2. So I'll leave that up. But next exercise, 9C part 2 on, what's this topic? Connected graphs. And the reason why I want to cover this is because even though we've already done this in matrices, there's one aspect of it that we didn't do a lot of, which was drawing a graph from a matrix. Okay, we didn't do a lot of that. So I figured it'd be good to do for this, just for this, and that's why we're covering it. Okay, so please be attentive for this one. So remember, an adjacency matrix is basically just a matrix list of numbers, but in the context of networks, it tells you the connections between those vertices. Okay, so it essentially, like I said, like what I sort of talked about, it represents a graph. Okay, so it's a bunch of numbers representing a graph. Each, you've got, remember, your rows and columns. So you got rows and columns, and represents a vertex in the graph. Remember, all your matrices in here are going to be square matrices. Yeah, the number of edges, number of rows and columns will tell you how many vertices you have. So if it's a 4x4 matrix, how many vertices? How many dots? If it's 4x4, 4. If it's 5x5, 5 dots. 6x6, 6 dots. Okay. So for this one here, we need to write down the adjacency matrix. So it's the same as how you would have always done your matrices. Okay, make sure you've got space for this. And because there is 4 vertices, it's going to be a 4x4 matrix. So A, B, C, D, and then A, B, C, D. Okay, give yourself space for this. So let's do it. A to A. Ooh, okay. What do we see here, guys? What's happening here? There's a loop, so that's going to be 1. I'm reading this as A to A, like that, or A to B, so I'm going that way. Doesn't really matter too much because all your networks are going to be bi-directional. Okay, you can go both ways. A to B, how many connections? I see 1 right there. A to C, there is none, no direct connections. Remember, it's just direct, straight to. Okay, not 2-step or 3-step, just 1 step. A to D, I see 1, easy. B to A, I see 1. B to itself, I see 1 as well. B to C, there is 1. B to D, it looks like there's 1. Yes, okay. C to A, there's none. Okay, no direct connection. C to B, I see 1. C to itself is 0, and then C to D, there is 1. So D is where it gets interesting. D to A is 1. D to B is also 1. Sorry, it's not interesting. It's the same. D to C is also 1. And then D to A itself is 0. Okay, so that's what our matrix should look like. And notice again how if you look at the numbers this way, so for example, these numbers and these numbers and these numbers, there's some sort of, what's the word for it, parallel happening to it because they're the same. So if you've done it correctly, double check that. Okay, pretty straightforward. Yeah, just make sure you understand the loops. We haven't worked with a lot of loops in these networks with matrices. So there's loops happening here. All right, let's do this one the other way around, which is we haven't really done much of this. Okay, so how do we then represent a matrix or adjacency matrix into a network? So always label. I like to label just so it's easy to work with. So this is A, B, C, D, A, B, C, D. Okay, it's 4x4. That means there's going to be 4 vertices. So 1, 2, 3, 4, and label your vertices. So I'll go to A, B, C, D, so that you know what's connecting to what. Okay, now we do the connection. So A to itself is 0. A to B, apparently there's 1. A to C, there is 1. A to D, there is nothing. B to A, there's 1, which is already there, so I don't have to draw it again. B to itself is 0. B to C, 0. B to D, there is 2. So you make sure you draw 2 edges there. 2 connections. C to A, there's already 1 there, so I don't have to draw that. C to B is none. C to itself, I see a loop there, so make sure you draw your loop somewhere. You can draw it anywhere, just as long as there's a loop happening. And then C to D, there's one. Don't forget that one. And then D, so you got D to A, there's none. Cool. D to B, there's already 2 there. 1, 2. So I don't have to redo it. And then you've got D to C. So there's already 1 there. I don't need to draw that. So there is my network for that matrix. That's technically it. Okay, so make sure you do the questions for 9C part 3. If you